Thanks so much for having me. I'm really excited to be here. I was just saying, I'm sure a lot of you signed up for this conference like 3 years ago. So it's fun to actually do this. And yeah, actually since then I moved here, so that's fun too. So yeah, I'm just going to be talking about our recent results. Once again, this will be posted on archive hopefully in a couple weeks with Ella Hiesmeyer, who's a PhD student at UC Berkeley. Okay, so first let me just talk about a general overview of what we're going to do. So the first main takeaway, and this has been done before, but is that if I'm looking at the edge eigenvectors and eigenvalues of a sparse random matrix, then really what I'm interested in are these local statistics surrounding high degree vertices. So we're going to talk about that a lot more. And then the second thing is that what we're really going to focus on is constant degree over training graphs. And in this case, we can't really use concentration measure type bounds, but we can use some more general bounds by being a little bit creative, and this will give us our eigenvectors and our eigenvalues.
These are of the adjacency matrix?
Yeah, of the adjacency matrix. Yeah, sorry, this is very like abstract. Right now. I'll be more precise. Okay, so why is this relevant? So this is a picture of me when I'm 10. This is my first school ID. And I tried to make a funny face, and I failed, and then I had this ID for 5 years. But I think the relevant thing here is that if you look at my date of birth, today is actually my 30th birthday. So I think for my 10th birthday, I played laser tag, so this is definitely a different vibe. But I think it's just as fun. But not relevant to the topic. Okay. So I'm just going to start with a couple of slides, just of very general background. So if I have a graph that induces an adjacency matrix, the adjacency matrix I put a 1 if 2 vertices are connected. I put a 0 if they're not connected. That's just the model we're going to look at. And in this talk, I'm going to go very flippantly back and forth. We're talking about a graph and then talking about its adjacency. Okay, and then the other thing that I'll just say very quickly, just as very brief motivation, is that solving these spectral geometry problems on graphs is fundamental to many problems and to many algorithmic questions in computer science. So yeah, long list. Obviously, it could be way longer. And so really, what we're gonna do is that we're going to do a large abstraction of this. And really, what we're going to talk about during this talk is just what is the average case structure of eigenvectors and eigenvalues in these graphs. Okay, so if I say average case, then it's probably not surprising that I'm going to be talking about Erdos training graphs. So for an Erdos training graph on n vertices, I have n choose 2 potential edges. And I include each one with some fixed probability p, and this will give me some distribution over graphs on n vertices. And for this talk, it's useful when you're talking about sparse graphs to talk about a g and d over n graph, where d is the expected degree of a given vertex, right? So just p equals d over n. Okay, so that's just a little bit of background. Okay, so why do we care, and how can we interpret the questions that we're going to be asking? Well, I have 2 eigenvectors here. So the x-axis is just the index, and the y-axis is the value of the eigenvector. And one is for a planar-clique graph, and the other one is for an Erdos training graph with no clique planar. Right, and the reason why we can use spectral geometry to find a planar clique, right? So this left-hand one is clearly a planar clique. We have this. If you look at the first two, I think it's 200 indices. The value of those indices is much higher, right? So really the reason why this works is that very roughly speaking, when I'm looking at a Planet Cleek, what I'm doing is that I'm taking my random adjacency matrix and then I'm adding approximately a rank one matrix to that adjacency matrix. And the point is that when I look at those two eigenvectors, so the eigenvector associated with the rank one matrix, and then the top eigenvector of the adjacency matrix, that those are far away from each other, right? So when I add them, when I do this addition, then I'm going to see a difference in the two eigenvectors, right? So really, this is a question about what is the structure of the largest eigenvector of an error training graph, and we can generalize this and think about there's a large class of questions, right, where really what we're looking for is what is the structure of this eigenvector, potentially even the largest eigenvector, and a fundamental question is the eigenvector localized or is it delocalized, right? So localized means something like on the left where once again this is just everything is a square value versus the index. So you can see the largest square value is something like almost a quarter of the entire mass. And then I have a couple which are slightly smaller, but most values are almost zero. Right? So this is a localized vector, and I want to differentiate this between something like on the right where you can see the scaling is very different. It's 10 to the minus third. And basically most values are around the same magnitude. Okay, and then the other fundamental algorithmic question that these eigenvectors and eigenvalues need to be able to say is once again I can think about how large are the largest eigenvalues, right? So this is for spectral partitioning, this is for random walks, etc. So really, I just want to say, okay, I have an average phase and error training graph. Then what are the optimal bounds in terms of its structure, in terms of the size, and then its localization. Okay, so along with this this motivation from computer science, there's also motivation coming from the physics side as well. So if we think about the Anderson model, so we can just think about this as I take my adjacency matrix of ZD of the d-dimensional lattice, and then I add some random potential, which is just a random diagonal operator to that. So the Anderson model asks, when I do this, then what is the structure of my eigenvectors? And the general intuition is that I'm asking for the transition at different energy levels, so for different eigenvalues, of between localization, which corresponds to being an insulator, and metal behavior, which is delocalized eigenfunction. So in general, we would expect we would expect near the edge of the spectrum to have this type of exponential decay, which is known as Anderson localization. And once I go past the edge, then eigenfunctions are more delocalized. So there's been more progress on the localized regime. This is definitely not a complete list, but it's been a very interesting, very fruitful problem. And just to be clear, what do I mean by exponential decay? I just mean something that looks like this, right? Where I have some root vertex, you could think about it, and as I move away from the root vertex, the values of my eigenfunction decay exponentially by some multiplicative factor. Okay. So once again, we expect this this change between delocalization to localization. So we can think about the same problem in different models. Like the original Anderson model, once again, it's been quite tough to think specifically about the delocalization phase. But once again, these are very non-trivial to even think about localization. So we can think about Bernoulli potentials for my V. Another interesting question is if I think about a random matrix where instead of something like GOE, my entries have heavy tails. which is a Levy matrix. And this is, once again, something that's been studied in terms of the transition between localization and delocalization. Okay, so the point is that we can study this, localization versus delocalization transition in all these different models, but actually we can even see this in error-friendly random graphs, specifically in the sparse regime. So for now, sparse just means smaller than polynomial. Okay, so let's first think about a dense graph. So let's say that my typical degree is greater than n to the 1/3. Then when I look at the edge of my spectrum, and also if I look at the corresponding eigenvectors, those will the statistics of those are going to emulate the statistics of a GOE matrix. So basically, if I have a very dense error-training graph, and I look at statistics, it's the same as if all of my entries were just Gaussian, which is kind of like the nicest thing that you could hope for. However, this isn't true for all polynomial. We do have this phase transition at n to the 1/3, and I no longer have GOE statistics. So the Tracy-Woodham distribution, if you know that, so that goes away, and now edge eigenvalues now have Gaussian fluctuations. Okay, so we're starting to see this different regime when d becomes smaller and smaller. So let's keep on going down. So now let's think about very sparse graphs. So if capital delta is the maximum degree in my graph, then there's this very nice result of Krivlovich and Sudakov who say that basically I have two options in terms of what my maximum eigenvalue is. Option one is, and sorry, this is for an error-training graph. Option one is that my top eigenvalue is d, and option two is that my top eigenvalue is square root of the maximum degree, whatever that maximum degree is. And this is true for any d. So let's think about what this means. Right. So it means that approximately, I really need to just think about two eigenvectors. The first eigenvector is just the all ones vector. And this will be the eigenvector that gives me eigenvalue d, right? Because once again, on average, every vertex has d neighbors. So if I take the all ones vertex, I'll approximately have quadratic form d, normalized, of course. And then the other option is that I just look at the star around the highest degree vertex. And that will have eigenvalue square root delta, right? And the eigenvector that corresponds to that eigenvalue is localized in the sense that half of its mass is on the central vertex. So let's just look at vertex 20. Half of the mass will be on the central vertex, and then the other half will be spread evenly through all of its neighbors. So this is kind of like the most extreme form of this localization that we could have. So another intuition that I hope that you can take away from this slide is that in some sense the largest eigenvalue corresponds to the highest degree vertex. And what I mean by this is that when we are tracking what is the highest eigenvalue, it's in some sense it's enough to think about what is the highest degree vertex. And this will be much more crowded. So, yes.
So this is also part of their theorem?
No. So their theorem is not actually about the structure of eigenvectors. Their theorem is just about the actual eigenvalue, the top eigenvalue. Yeah. This is just more like, sorry, I should be more abstract than me. But like abstractly, like this is at least the intuition that I get from this. Yeah. And this will be confirmed. Okay, and to be clear, this eigenvalue on the right is what happens in the very sparse regime. So as d becomes smaller and smaller, then the maximum eigenvalue will be determined by this maximum degree. Okay, and another like intuition from this, right, which once again will become more concrete. But if we want to think about the fluctuations of eigenvalues in this very sparse regime, it's potentially related to the distribution of the square root of the largest degree. For example, like the largest degree of a random graph, right? This is some random variable, right? So in our hope, I suppose, is that the distribution of this random variable is tied to the distribution of whatever the largest eigenvalue is. Okay. So this is a statement, privileged Sudakov, this is a statement about the largest eigenvalue. And once again, we have this intuition for the largest eigenvector as well, that it's going to be localized in this sparse regime. But the thing is that this is not something that's specific to the #1 largest eigenvalue eigenvector, right? That if I look here, so the x-axis is my index, the y-axis is just the infinity norm of an eigenvector, right? So what we see is that in the middle, so this is surrounding 0, I have many delocalized eigenvectors because they have small infinity norms. I do have some localized eigenvectors. In fact, I even have one with infinity norm 1 that just corresponds to disconnected vertices in my graph. But to have near the edge, I must have higher infinity norm, right? And once again, this is not just a phenomenon of the largest eigenvector. This is a phenomenon of some window near the edge. Okay, so when do we start seeing this type of localization? Well, the transition that we get from Privileged-Sudakov happens at when d is approximately square root log n over log n. That's when the average degree is approximately equal to the square root of the maximum degree. However, we start to see this more localized behavior around log n, and for a couple of reasons. One is that this is a threshold for connectivity. So this is the original work of Erich and Ring. But moreover, it's a threshold for concentration of degrees. So basically above d equals log n, all the degrees in my graph are approximately the same. But below d equals log n, I start seeing large fluctuation, large variance in terms of the actual degrees in my graph. Okay, so this very sparse regime is also something that's received a lot of attention. And there are a bunch of results. I won't have time to list them all, but let's just say that there's a series of results that increases this intuition that if I'm in the very sparse case, I continue this correspondence between eigenvalues and high degree vertices. Moreover, Alt-Ducatez-Knowles showed that a transition between the delocalized phase in the bulk of the spectrum and then the localized phase near the edge of the spectrum, assuming that d is O of log n, and then bigger than this like Privileged-Sudakov threshold as well. Moreover, we can consider large deviations of these eigenvalues in a couple of very nice works by Bhattacharya and Ganguly for the edge eigenvalues, assuming we're in this sparse case. Okay, so I don't know what I just did. Oh, we're good. Okay, so what's the general theme here? Well, I have the Anderson model, I have Levy matrices, I have sparse error-restraining graphs. And the point is in each of these, there's some statistic around which my eigenvectors will localize. So for the Anderson model, it will be these small clumps with large potential. For Levy matrices, it's these large entries in my matrix. And similarly, in sparse Erdős-Rényi, it's going to be these high degree vertices. Okay, so just I'll talk about one more result before talking about what we did. So Alt-Ducatez-Knowles, they show the following. Well, if I have this, if D is within this window, so once again, it's just like some constant times, it's at most some constant times log n, and it's bigger than log n to the fourth, then I can say something very specific. Basically, I can tell you almost everything about these high eigenvalues, high eigenvectors. First of all, if I fix k, the top k eigenvalues approximate a Poisson point process. We'll talk about this more. And moreover, this Poisson point process is governed by, once again, the combinatorial statistics around these high degree vertices. Secondly, the eigenvectors of the top k eigenvalues are exponentially localized. So that's this Anderson localization that we saw before. Okay. So the way that I became interested in this question is that so this threshold on the right, this d star log n, this is something that the same team studied before. It's very natural, but we weren't quite sure whether this was a natural bound or not. This log n. Specifically, we were really interested in if I have a constant degree, then what's the structure of eigenvectors, eigenvalues then? So what we show is the same behavior through the constant regime. So what we show is that if d is at most logs of 1/4 n, and at least logs of -1/8 n, and for any fixed k, then we have this exact same behavior. The top k eigenvalues approximate a Poisson point process based on combinatorial statistics, and eigenvectors of the top k eigenvalues are exponentially localized. So to be clear, this result is new only when d is at least log n to the fourth. Right before it's this Alt-Ducatez-Knowles result. It turns out that when we do it, it works up to this higher threshold. So our goal was to deal with constant degree, we keep as a bonus we can even get subconstant average degree.
By the way, one question. So this exponential localization you explained is the root of that, where it starts to decay.
Yes.
The high degree vertex.
Yeah, exactly. It's basically for the top k eigenvalues, I take the k vertices of highest degree, and then each one has a corresponding eigenvector which has exponential decay around it. Yeah, that's more or less what's up. Okay. This is the results. Are there any other questions about it before we go forward?
So you're literally saying like the top 10 eigenvalues come from exactly the top 10 degree vertices?
It's a little bit more complicated than that because I could have some degrees be the same, but roughly yes.
Okay. Yeah, except for ties, that's actually.
Yeah.
Okay.
And we, as we'll see, we can break ties. Yeah.
Like, is there any intuition like don't like cross or something? Like maybe a degree like 100 vertex crosses a degree 101 vertex.
Sure. Yeah. Let me see whether I answer your question, and then if not, we can talk about it more. Okay. Any other questions? No? Great. Okay, so how do we do this? Well, we try to follow the same general outline. So what does that mean is that, we know that these local statistics should govern our top eigenvalues. So let's approximate these top eigenvalues in neighborhoods of our highest degree vertices. That's step one. And then step two is just take everything else and show that nothing else can get in that region, right? And then that's sufficient. Okay, so let's talk about what we did for the first part. Okay, so what is the structure of these high degree vertices? Well, there are two really important things that I want to start with. which is that, first of all the high degree vertices in my sparse error training are very far away from each other. Okay, that's good. They don't form, these tight clusters. That would be a problem. Secondly, in these sparse graphs, locally, their neighborhoods are all tree-like. And yeah, this is something that you can prove just with, union-bound type arguments. Yeah. Okay, so that's great. So we know that with these localized eigenvectors, really, the eigenvalue is just governed by whatever the local geometry is, whatever the degree sequence is around these high degree vertices. Moreover, these local geometries, so basically the structure around each of these high degree vertices, because they're very far away, they're approximately independent. And because they're approximately independent, this is what creates our Poisson point process. Because it just asks, what's the probability that I have a given local geometry, and then a given local geometry gives me my eigenvalue, some specific eigenvalue. Okay. And we can say something similar, right? Is that because everything is far apart, and because of this independence that we said before, and moreover because these eigenvectors on these small regions, they're localized. Once again, there's like almost independence, and the eigenvectors in the overall graph will inherit the structure of the eigenvectors of these small neighborhoods. Okay. So what do Alt-Ducatez-Knowles, what do they do? So they say, okay, let's say that I have a local neighborhood that looks like this, right? So this blue vertex is my high degree vertex. Then what they do is that they say, well, before we were talking about just the degree of this vertex, but it turns out that's actually not enough. What we're going to do is we're going to consider two statistics. The first statistic is just the degree, which I'll denote by alpha x. And the second statistic is the number of vertices at distance exactly 2. Right? So, and that's what we call beta. So in this case, x is just my blue vertex. The green vertices are correspond to alpha, so there are 6 of them. And then the purple vertices correspond to beta, there are also 6 of them. Okay. So what they do is that they say, okay, in fact, this is all that we need to know. It's just alpha and beta. So once again, previous work was only considering alpha, and we have the second parameter now. And then they do something which I think of as an educated guess, where they say, well, I know alpha, I know beta, then what's the most likely thing that can happen? Only knowing alpha and beta. Well, the most likely thing that can happen is that I have an alpha, beta, d, sorry, this should be beta over alpha, regular tree. So what do I mean by this? I just mean that I know that the degree of my vertex is alpha. That's fine, that doesn't change. I know that the total number of vertices at distance exactly 2 is beta. So let's divide those vertices evenly amongst each of my alpha vertices. Right? So it's really an alpha, beta over alpha, d regular tree. And then I know that the expected degree is d. So every other vertex in my local neighborhood, just give it degree d. Okay. And the point is that if I take an alpha, what they call an alpha, beta x over alpha x, d regular tree, then this is the corresponding eigenvalue. This is the largest eigenvalue of this tree. You can see that, the first order term is just alpha over square root alpha, which is like what we had before. But there's this adjustment factor that gives us higher levels of accuracy. Okay, so this is the educated guess. Is that you're saying, okay, if I know alpha and beta, probably it will look something like this. Oh, did it again. Okay, so specifically, once again, if I have some local neighborhood, you can think about it as I take a neighborhood that looks like this, and then I do, I take out, I cut and paste and move stuff around, and what I end up with is something which is regular around vertices at level 1, and then D beyond that, right? So everything else goes away. Okay, so the point is that when D is sufficiently large, when D is bigger than log n to the 4th, then this educated guess is fine by concentration measure, right? The point is that every vertex that I look at, it will approximately have the properties that we want. But the problem is that when D is smaller, then this concentration breaks down. I start seeing larger and larger fluctuations, and actually there's a non-trivial difference between my true eigenvector and the eigenvector that our educated guess of this alpha x beta x over alpha x d regular tree. Okay, so this was kind of like our starting point. So what do we do? Well, like I said, the degree sequences surrounding high degree vertices is becoming more volatile. But the thing is that we actually gain something as well when D becomes smaller and smaller. And the thing that we gain is that the typical ratio between the highest degree vertex and all of its neighbors becomes larger and larger. So the point is that as D decreases and our graph begins to fluctuate, the statistics begin to fluctuate more, it also relies less on these parts that are actually fluctuating. Okay, so to be more specific, we know that if for any D in this regime, so if it's at least log to the minus Cn and at most log to the 1 minus epsilon n, then the maximum degree stays in the same order. It's always of order log n over log n. And this is just the balls and bins paradigm. So the point is that, well, once again, as D decreases, this max degree is decreasing, but it's decreasing at a very slow rate. Okay, so how do we get past this problem? Well, we're going to not guess. We're going to just say whatever our neighborhood is, that's fine. Let's just truncate at some fixed radius that we can decide later, and then that's going to be the top eigenvector, top eigenvalue of that truncation is going to be what we do. That's fine. Let's just work with that. So you can think about it as thinking about the entire local geometry. Okay, so for example, I have this local neighborhood here, and I'm just going to truncate after some fixed radius. Okay, so this is very intuitive, and then you might be like, well, why wouldn't you just do this in the first place, right? But the thing is that there are a lot of complications that we get from doing this. So first of all, let's talk about the good part. The good part is that, first of all, I need to show this. I have no idea what my eigenvector and my eigenvalue are. But if I can show that the top eigenvector is localized, then when I do this truncation, because I only do the truncation at the boundary, my error of approximation is very, very small. Right? If I have exponential, basically like, what I'm doing is that I'm taking some neighborhood that looks like this, and my point is that when I do this truncation, my error is only going to come from all the values at the boundary. So if I have exponential localization, then this error is going to be very, very small. Okay, but the problem is that now we have at least for now, we have no information about our eigenvalue or our eigenvector. Right? We just said, we take an arbitrary tree. Whereas, for this educated guess that was done before, there's explicit eigenvalue, there's explicit eigenvector. Okay. So how are we going to do this? So once again, we just want to use these local combinatorial statistics. And what we're going to use is, once again, what we used before. It's that neighborhoods are trees, and then because D is small, the central vertex has a much higher degree than all other vertices. And, more or less, along with a couple other things, this ends up being enough. And the point is that if I have any tree graph, any eigenvector of any tree satisfies a recursive eigenvector equation, and then this can get very gross very quickly, but the point is, because the central vertex is much higher degree than everything else, that it can be approximated just by the first couple of terms. Okay, so what exactly are we doing? Well, let's pretend that I have my high degree vertex x, which is up at the top, and I have some arbitrary vertex v in the middle of my tree. Well, we know that the eigenvector equation needs to be satisfied at v, just like it needs to be at every vertex. And the thing is, I want to write it in I'm going to rewrite it in a suggestive way, and the point is that what I really want is I want localization. So what I want is for the eigenvector equation at v to be almost completely governed by its neighbor up top. Right? This is kind of like the ultimate localization. Is that because I have the highest value at x, and then I'm exponentially decreasing at each level. So theoretically, the value at u should give me all of the information about the value at v. Okay, so that's, how do we actually show this? Well, we actually induct from the bottom of the graph back to the top. So the bottom of the graph, if let's say that v were a leaf, right, then what I said would be true. If v were a leaf, then clearly the eigenvector equation is completely determined by its neighbor above it, because that's the only neighbor, right? Okay, and then the point is that if that's the case, then this sum here on the right is small. And moreover, the number of terms in my sum is also small because what we assume is that the max degree in the neighborhood is small. Okay, so that's a very rough approximation. Okay, so for the eigenvalue, it's a little bit more complicated. It kind of becomes a bit of a nightmare. But we just do the exact same thing. We say, once again, let's just use the eigenvector equation at every single vertex. And we get this continued fraction, which once again, this will be something that's satisfied by every tree graph. And the point is that if I write out this continued fraction, if I expand everything into infinite sums, right, then I get this nested series of, if I'm looking at a radius r ball, of r infinite sums. Okay, so this is gross, but really the thing to note is that I have 1 over lambda squared in each of these, and what we said is that the degree of the central vertex is much larger than the degree of any other vertex, right? And moreover, I know that this lambda squared, which is like the test eigenvalue squared, remember that we said that like lambda is approximately equal to square root delta, right? So lambda squared equals delta, or sorry, is actually greater than or equal to. So what that means is that each of these geometric series is exponentially decreasing. So what this means is that at each level we can actually just approximate each of these exponents by if we set all of them to be 0. And then so I can set all of them to be 0, get some approximation. If I want tighter approximation, I can toggle the first few to be non-zero. And the point is that what ends up being sufficient, for our problem is if I just basically toggle like 3 exponents. And what we get is alpha plus beta over alpha, and then plus some higher order terms that basically correspond to the ball of radius 3 and the square of degrees on the first level. Right? It's basically like the next order moments around this graph. But the point is that, okay, so this ends up being sufficient for our problem, but if I want to get any accuracy that I wanted, I could just keep on looking at this equation and take away as many terms as I need. Okay. So, so we have explicit formulas for eigenvectors and eigenvalues. So what we need to show localization, we need to show that these statistics don't intersect, right? So specifically that these statistics are far away from each other, so I couldn't have an eigenvector which is like half on one ball, half on the other ball. And we end up needing very tight probability bounds for this problem. Okay, so specifically, we end up just needing tight probability tail bounds on the Poisson. Okay, so I mainly just wanted to highlight this part because I thought it was really cool and I didn't know this bound before. Because we were looking for this, and then we realized that actually Terry Tao had a blog post about this, like this is December of last year, about this exact topic. And so what this gives is Poisson tail bounds, which are tight up to a constant. And he wrote this because he was like, oh, like this is kind of in the literature, or it's implied in the literature, but it's not given anywhere explicitly. So I also just kind of wanted to advertise this bound because it was super useful. But the point is that I take this h of x term, which is standard from Bennett's inequality. Then there's some constant such that if I take e to the minus Poisson lambda, e to the minus lambda h delta x over square root 1 plus this other thing. This gives me the probability that I'm delta lambda above my expectation. So kind of, at least to me, the standard Poisson tail bound is this e to the minus lambda h of delta, which is Bennett's inequality. And the point is that if I add this extra term, which depends on delta, then this actually becomes tight up to a constant. And so this is what we use to show that we don't have intersecting neighborhoods. Okay, so that's the first step. I'm almost out of time, but this part's pretty quick. So we use the combinatorial decomposition from Kolovich-Sudikov. Okay, so yeah, sorry. The second part is I want to show that nothing else interferes, right? So in this low degree case, we could just use Kolovich-Sudikov, and the point is that the way that they actually show their theorem is by decomposing their graph into like 6 parts, right? And they show that each of the 6 parts, or 5 of the 6 parts, have very low spectral radius, and only 1 part has spectral radius, which should contribute to the top eigenvalue, right? Assuming that square root of d is much bigger than square root of delta is much bigger than d. Okay, and this part is just a bunch of stars around high degree vertices, which are spread out. So this is great, right? Because if my degree is sufficient, basically, if I consider the error of this result, and I just think about the degree of these disjoint star graphs, then it automatically tells me that if the degree is sufficiently small, sufficiently bounded away from the max degree, then I don't need to worry about anything whatsoever, anything in that region. Okay, so to put everything together, what we do, which is the same thing that's done by Alt-Ducatez-Knowles, is that we do a block decomposition, and we do it where highest degree, intermediate degree, lower degree, everything else. The point is that for these first two, the highest degree and the what's called the intermediate degree, we do this eigenvector eigenvalue analysis that we talked about before. For lower degree, we end up using a test eigenvector, which has worse error, but it ends up being fine. And then for the everything else, we just use the Kolovich-Sudikov bound. Okay, so that's the end of the proof sketch. So let me talk about a couple of consequences of what we've done. So like I said before, I can guarantee with high probability that the maximum eigenvector, or this should be eigenvalues, are lexicographically ordered in terms of alpha x, beta x, in terms of these first two statistics. So if you ask me for any k, what's the kth largest eigenvalue? I can say, well, it's going to be it's going to correspond to the eigenvector localized around the vertex with the kth largest alpha x, beta x pair. Now, note that this is actually specific to our regime, to our very sparse regime, because in the higher degree regime, I don't get this nice exponential, I don't get quick enough exponential decay to guarantee this. So it could have, these fluctuations between, a vertex of degree delta minus 1 versus a vertex of degree delta. But the point is that the concentration bounds that we get in this very sparse regime are tighter than the actual difference that we get by shifting alpha x by 1.
This is for what K again?
Oh, so this is for any fixed K. Really we can set K, equals, it works for K equals log n to the little o. Right? So the first K eigenvalues. That's cool. Okay. Okay, and then let me just quickly talk about fluctuations, like we talked about before. And the point is that fluctuations, and this is once again in the same in the as was shown by Alt-Ducatez-Knowles in the slightly larger D regime, is that there's this very interesting dichotomy here where because everything is governed by alpha x and beta x, there are two options. The first one is that alpha x is random, right? So the max degree, so it's a result of blah blah blah. Basically, the max degree with high probability is one of two things. And if we're mainly it's u and u minus 1 for some fixed u. And the point is that if we're in a regime where there's actually we're bound away from 0-1 probability of being u versus u minus 1, then the top eigenvalue is just governed by the fluctuation in alpha. But we can definitely be in a regime where alpha is that delta, the maximum degree, is deterministic, right? And in that regime, then the eigenvalue fluctuations are governed by beta. So they're governed by a much smaller, then they have much smaller variance, and moreover, the distribution just becomes the distribution of the maximum of Poissons. Okay. Okay. Now let me just say quickly. So there are, like I said, this doesn't generalize to the previous work, and specifically there are a couple of natural obstacles to this truncation method at this equivalent which we call down at d equals square root log n over log n. So we need some kind of if we did want to do it, which it would just be for curiosity because we already know it in this regime. We would need some extra work there. Okay, so then just to conclude, we can limit our error by truncating. We can have an explicit dependence of the edge eigenvalue on local statistics. Once again, we can go as far as we want, and the bound that we get is this thing, which isn't necessarily basically this is what the typical eigenvalue is going to look like, which isn't necessarily that nice, but yeah, it does completely describe the regime. Okay, so I'm out of time. Basically, just the questions that I had were, how far can this go into the bulk of the spectrum, right? Because Alt-Ducatez-Knowles talk about this like semi-localized regime. So can this truncation method still work there? And then, I always have questions about delocalized eigenvectors and specifically what's known as nodal domains of delocalized eigenvectors. But that's kind of a separate question. So I'll end that. Thanks.